So as was mentioned, I'm going to talk today about Perlmutter, which is our supercomputer coming at NERSC, which is in Berkeley next year. So I just wanted to start off by explaining to those of you that don't know what NERSC is. We are the National Energy Research Scientific Computing Center. So we're the mission high-performance computing facility for the Department of Energy Office of Science. So if you have a grant from the DOE to do research into chemistry or physics or biology, and that work involves simulation, you can get time on one of the machines at NERSC to do those simulations. So you can see represented up in the top right-hand side of the slide, that's the kind of things that we do. There's some simulations of the cosmic microwave background, or of stars exploding, or of turbulent flows. One of the things we're doing more and more is we're also doing data analysis to support the Department of Energy's experimental and observational facilities. So the example shown in the bottom right here, this is the synchrotron, which is also a Berkeley lab. One of the things we're doing is directly connecting the beam lines at the synchrotron to the supercomputer and actually moving the end station from what used to be just a PC sitting at the end of the beam line right into the supercomputer and actually applying supercomputing level resources to solving the data analysis problems for those kind of experimental facilities. So NERSC has a dual mission. The first piece of it is to advance science by providing computing resources. So we have currently on the floor two big Cray machines, Edison, which is the one at the bottom there, and Cori, which is the one at the top there, which I'll talk about a little bit more in a minute. We also work quite closely with the vendors of high-performance computing systems and the processors and the storage and the interconnect and all the kinds of things you can think of there. And the goal there is to try and deploy a cutting-edge advanced architecture system such that our users get the maximum amount of performance they can in a given time frame to get their science done. But we also try and trade that off with productivity to make sure that their mission to advance science is also achievable. So the system I'm going to talk about today is Perlmutter. So this is the overall DOE roadmap to exascale. Summit and Sierra, the ones in 2018, so that's the current number 1 and number 2 on the top 500 list. Perlmutter, which is the one I'm going to talk about today, is coming next year in 2020. Some of you may have seen the press release came out on Monday for the Aurora machine, which is coming in 2021 at Argonne, which is up there in the top right of the slide. So this is the NERSC systems roadmap. So one of the things we have to think about as we move forward in time here is to ensure that our users continue to get increasing performance as you get go further along in time and you move towards from the end of Dennard scaling, which really happened around 2004, where you went to multi-core processors, to somewhere around 2024-ish, 2028, where we'll be moving into kind of a beyond Moore's law era of computing. And it's clear that in order to keep getting increasing performance in processors, we need to use more and more energy efficient architectures. While at the same time, we also need to make sure that our users are productive and that the programming models that they use enable them to be productive and the architectures don't impose too great of a burden on them in order to be able to use them efficiently. So in order to begin this journey, one of the things that NERSC did in 2016 was we deployed an Intel Knights Landing machine. So that has more than 9,600 Intel Knights Landing processors on it. So that is, relatively speaking, compared to a regular 2 or 3 gigahertz fat core machine, that's a pretty energy efficient architecture. It has 68 cores on it, and it also has 16 gigabytes of RAM. So that was the high bandwidth memory, excuse me. So that was the machine where we began working with our users to begin them along this pathway to optimizing their code, adding more and more parallelism into them. So we're going to continue along that pathway with the Perlmutter machine. And I'll talk a little bit more in detail about the architecture of this as we go through the talk. It has two kinds of nodes. It has some CPU-only nodes, which are based on AMD EPYC Milan processors. It also has some GPU nodes with future NVIDIA GPUs in it as well. So this is a little bit more detail about what the GPU nodes look like. They are going to have 4 GPUs, and they will be based on the Volta Next processor. If you want to Google what that might be, you might find more out there on the web than I'm allowed to say here in a public forum. But anyway, these are the specifications of a Volta that you can go by today. As you can imagine, the one next down the roadmap has got bigger numbers and they're better and all that kind of thing. One of the cool things about this machine that I haven't really talked about, but I will a little more in a little while, is it's based on a Cray Slingshot interconnect. And one of the good things there is we can actually put 4 NICs inside this node. So each of the GPUs will have its own independent network card that it can use in order to communicate over the network. So that provides us a much richer balance of network bandwidth to compute performance than has been seen in recent supercomputers. So that's a really good thing. Overall, the GPU partition will be roughly 2 to 3 times the performance of our Cori machine today. So we'll also have some CPU nodes. These will be dual socket AMD Milan nodes. So Milan is the AMD processor that's one after Rome, which is the one that was just announced last October and will be available sometime later this year. So as before, these are the specs for Rome. You can imagine the ones for Milan are a little bit bigger and better. So one of the interesting things about this architecture is there's the processor architecture. There's a picture of it over there on the bottom right-hand side. It's actually a multi-chip module. There's one big I/O die in the middle, and then there's going to be 8 separate dies with the CPU processors on that are arranged around the outside. The CPU dies are actually in the latest technology. They will be 7 nanometer plus process, whereas the I/O die is actually going to be in 14 nanometer. So that's actually a good thing from our perspective because it saves cost. And also from a performance perspective, because you don't really gain significant amount but for the I/O functionality between the 14 and the 7 nanometer dies. So as I said, we decided that we were going to deploy GPU nodes and CPU nodes. So one of the questions is, well, how do we decide how many CPU nodes and how many GPU nodes we would actually purchase? So in order to figure that out, we looked at what applications are actually running on our machine today. So as I mentioned on the second slide, NERSC actually has a large number of users. We have over 7,000 users, and we have over 600 codes running on the machine. But what you see is that the large number of codes are really in the long tail of the distribution. So 3 codes make up 25% of the workload. 10 codes make up 50% of the workload, and 30 codes make up 75% of the workload. So if we can understand the GPU readiness of just a relatively handful of codes, we can understand how well we could use GPUs across our whole workload. So that's what we did. We went out into the literature and we talked to the authors of the particular codes and looked to see if how we would class the level of GPU readiness. And this is how the pie chart breaks down if you label the applications into codes that are already running on GPUs today. Enabled means codes that are parts of the codes have been running on the GPU today. There's a paper or two or looking at the key kernels within them. A proxy means that there is a code in a similar area to that one that's already running on a GPU today. So if you see, and you look at that, you see, well, roughly half are running on GPUs today, depending on how you count. So the next question we said to ourselves was, well, can we be a little more quantitative about this analysis? So what we did was we created a benchmark suite to represent the workload, and the list of the codes that we used over there were on the right. So we had 5 codes that we found that were GPU enabled, and then we completed the benchmark suite with just 3 codes that we said were only running on the CPU. And then we used this metric we call the scalable system improvement, which really is allows you to measure the aggregate performance of a supercomputer. So what it tells you is the performance of your supercomputer of tomorrow relative to your supercomputer of today, and that is a product of the amount of extra work you can get done on the supercomputer of the future, because A, it's either bigger, or B, it's faster. And so what this metric here does is it takes the average of the performance of all of these 8 codes relative to this original reference performance. So then what we did was we set the GPU node performance to 10. So we just said the GPU node will perform 10 times as fast as the CPU node on each of the applications that are GPU optimized. And then we calculated what the optimal value of this SSI would be for different GPU to CPU node cost ratios. So that's what you see on the right-hand side here. The red curve is for when the GPU node costs 8 times the amount of the CPU node. The blue curve is for when it costs 6 times as much, and the green curve is for when it costs 4 times as much. So as you can imagine, there is a point at which the GPUs are so expensive that they're just not worth buying, right? And that's roughly what the red curve there is corresponding to. So, and as they get cheaper, going to the blue and to the green curve, you can see that the optimal amount of money you would spend on your GPU nodes is different, and it's a function of the cost benefit, essentially. So in this question you'd ask yourself as well, is 10x per node for a GPU node to a CPU node a reasonable performance projection out in 2020? So what we did on this analysis was we instead instead of varying the price of the nodes, we fixed the price of the node at 8-to-1 GPU to CPU, and this time we varied the speed up. So the red curve on here is the same as the red curve as it was on the previous slide. You'll see that if the speed up is only 10 and the price ratio is 8-to-1, then it's not worth buying, because some fraction of our codes in our workload are not being accelerated on the GPU. Only 5 of 8 are in this particular example. If you increase the speed up, we see in the blue curve, to 20 for a GPU node over a CPU node, you can actually see at this point there is actually a sweet spot at which you would get a cost benefit for buying a GPU optimized, some GPU nodes, and then similarly if you make the speed up 30, you would see an even greater benefit for buying some GPU optimized nodes. But as you can see, on the x-axis, what we're plotting is the budget of fraction of the budget spent on the GPU node. So if we're in a world where not all of our codes can use the GPUs, we're never going to be a maximum over there as 1.0 where we spend all our money on GPU nodes. We're always going to be somewhere in the middle. The point of this kind of analysis is that it can tell you where you should be in between the 2 extremes of no GPU nodes or GPU nodes. And there's a lot more detail in this reference at the bottom of this, that's written down in the bottom of the slide here. So given that we have 7,000 users and more than 700 codes, one of the things we've been thinking very carefully about is how we help our users get up and running on the Perlmutter machine. So one of the things we started with the Cori machine, the Night Landing machine, which came in 2016, was something we called the NERSC Exascale Science Application Program, or NESAP. And what we did there was we engaged with 25 application teams and hired some postdocs to work with them to help them port their codes over to the Knight's Landing architecture. So there was kind of this is kind of a breadth and a depth strategy. We have a we have a depth strategy where we engage very deeply with the kind of codes that use large fractions of time on our machine. And at the same time, we develop a large number of lessons learned and documentation and training that we can use to help the broad swath of our users actually get their codes tuned and up and running on the energy efficient architectures. So when we did that kind of work in the past, this is the kind of performance results we achieved, which is the plot on the far right there. You see and this is a relative measure of performance. So you'll see when we started on the Edison machine, the users ran their code, they get a performance of 1. If they then optimize, just take that same code and drop it on the Knight's Landing processor, then maybe it ran a little bit faster on average, but not so much. But when we then optimized for the Knight's Landing processor, you see we got over 3 times speed up. But one of the things that was really great was that those performance increases actually helped you back on the old machine, on the older architecture, because you were identifying more parallelism, you were removing serial bottlenecks, you were making the code more amenable to vectorization, and all the kinds of things you need to do in order to optimize performance on whatever architecture you're looking at today. So we're going to have a similar kind of thrust of work when we're looking at the Perlmutter machine for GPUs, tuning the application for GPUs. The thing that's going to be a little bit different is obviously there's heterogeneity now. There's a GPU and a CPU, whereas before the Knight's Landing was a self-hosted kind of a machine. And a GPU, you really need, probably, depending on how you count, you probably need about an order of magnitude more parallelism, at least, in order to fully exploit the abilities of a GPU, even relative to a many-core CPU of today. So one of the things we're going to try and do is to do that in a performance portable way, so that the users can take their code that they modified originally from Edison to work on the Knight's Landing and move it on to the Perlmutter machine. So one of the things we did was ask our users how are they actually doing that today. And what we found is that nearly all of them are using OpenMP in order to increase the unknown parallelism of their applications. And so there are some CUDA users and a few OpenACC and CUDA Fortran users down there in much lower percentages of response. So our strategy is really going to be based around OpenMP. We're going to work around using the OpenMP 5 specification. One of the things that does is it adds in a lot of extra features for accelerators, which make it a lot easier to use heterogeneous architecture than previous OpenMP versions of the specification. So we're going to work very closely with NVIDIA in order to make sure that happens. So one of the things we're going to do is look very carefully at which OpenMP features make sense to work on the GPU. Rather than just blindly implementing the OpenMP 5 standard, we're going to look at examples from applications in the NERSC workload as well as from the broader community and prioritize which features of the OpenMP standard should be implemented first on the GPU. So if there's anybody out there who has any opinions on this, please let us know. We're certainly interested in soliciting feedback from the whole vendor community about what kinds of pieces of the OpenMP standard you would like to see prioritized to be running on the GPUs. Or conversely, if there's things in the OpenMP standard that you really, really believe should not be ever put on a GPU, we'd like to know that as well. I'm sure that somebody in the audience has an opinion on that. So we announced today that we actually signed a contract with NVIDIA to do this work. So that's actually a really exciting thing for me personally. It's one of the first times that NERSC's actually engaged with a vendor and done a non-reoccurring engineering project like this. So that's a really good thing, and I hope it's the first of many more to come. So we're also engaging with the community to try and define the future of performance portability across all different kinds of architectures. So as I already spent a lot of time talking about PGI, and as I said, about OpenMP, and as I said, we'll be working with PGI and NVIDIA to enable that to work on the GPUs. We're also starting to get more and more engaged with the C++ community, especially some of the features and looking at some of the features in C++ 17 that are really designed to enable people to get more and more parallelism out of their application. We're also part of the OpenACC endeavors that are going on. And there is, for anybody who doesn't know, there's a Department of Energy Performance Portability meeting is actually next week in Denver. If you're interested, please keep an eye out for that. There's a lot of interesting talks there on this topic. So one of the other really cool things about the Cray machine is that will come with the Cray Slingshot network. So this is Cray's new interconnect that they announced at Supercomputing last year, Supercomputing 2018. This is a network that's sort of in the tradition of the HPC networks that Cray has provided in the past. It's really designed to run simulations at scale. It has very low latency and it has very high bandwidth, and it has many MPI performance enhancements. One of the things that's really annoyed us about Cray and other people's networks, in fact, in the past, has been this kind of thing you see up in the top right here. So this is just running the same application over and over and over again on the machine, just running with a cron job every day, and plotting the runtime as a histogram. So what you see is that most of the time it runs at the expected amount of runtime, which is what you would expect. Every now and then, about something between about 1% of the time, it runs 3 times slower than it should do. And that's really, when you look into it, it's really just due to congestion and contention for resources on the network. So one of the really good things about the Slingshot machine is that we'll actually have some pretty sophisticated congestion control mechanisms and some new adaptive routing mechanisms to actually minimize this tail latency. So that's a really good thing that will make our users much happier than they are on our Cray machines today, as well as other vendors' machines. Second thing that's really interesting about the Slingshot network is it's actually Ethernet compatible. So for the HPC piece of it, it uses Ethernet compatible packets. For the regular Ethernet piece of it, it will also forward and route TCP/IP packets just within the network. So if you wanted to, you could pick up your laptop, take it down to the machine room, and plug it into the machine and just start connecting and moving data around in the supercomputer. I don't think we're going to let our users do that, but they could, in principle. Excuse me. I don't know where you'd find a laptop with an Ethernet port on today to be able to do it with, but anyway. But this is a really good thing also for some of the processing the experimental data use cases that I talked about on the first slide. It really blurs the line between the inside and the outside of the machine. So what happens today is there's really kind of this monolithic brick wall. You're either inside the supercomputer or you're outside of it. And if you want to go from one to the other, you have to tunnel through a bunch of different protocol changes, through a bunch of different gateway nodes, and it's very complicated and cumbersome. What you'll be able to do with this machine is just to seamlessly send the packet all the way from your beamline or your accelerator, which could be halfway across the country, straight directly to either the file system or the memory of the compute node in the machine. So that actually is a really good thing. it should allow us to get guaranteed quality of service from outside of the building right into the compute nodes. Which if you're doing an experiment at 3 a.m. on a beamline somewhere or a telescope, you don't really want to have to wait for the supercomputer to get the data to the right place. So one of the other nice things about the Perlmutter machine is it will have an all-flash file system. One of the things we did on the Cori machine that I talked about earlier was we deployed a burst buffer. So that was really a 1.5 petabyte flash file system that went at about 1.5 terabytes a second. So 1.5 petabytes is not really that much capacity for a 30 petaflop machine. So really, a lot of the people that use that resource got some really nice bandwidth out of it, but they couldn't keep their data on it for very long. One of the advantages of, one of the things that's happening between 2016 when we deployed the Cori machine and now when we're deploying the Perlmutter machine is that the price of flash has gone significantly down, especially in a dollars per gigabyte sense. So what that allows us to do is to deploy a substantial 30 petabyte flash file system with the machine. So that's a really good thing. It will allow users to keep their data around on the file system for days or maybe even weeks, rather than having to move it in and out quite often. Second thing it allows us to do is to get a really good bandwidth to this file system. So it will probably do quite a bit north of the 4 terabytes a second that's quoted on the slide there. And there's absolutely no way you would be able to do that in a similar cost envelope with spinning disk in this time frame. So that's a really nice thing. And should help our users out who have I/O-intensive and data-intensive workloads. One of the things we've done in the past is asked our users what their wish list of things they could get from NERSC was. Usually their number one answer is they would like more compute time. The number two answer is they would like better I/O. So this is really a game-changing technology there. We don't often see factors of 4 or 5 in bandwidth or in capabilities happening between old machines and new machines. We'll also have a community file system based on regular spinning disk that will be for longer term storage. That will be about 200 petabytes and about half a terabyte a second. So the NERSC 9 machine is called Perlmutter, and it's named after Saul Perlmutter. Saul is a staff scientist at Berkeley Lab. He won the 2011 Nobel Prize for discovering that the expansion of the universe is accelerating. So the way in which he did that was to look at supernovas and to figure out what their redshift was. And they did a lot of that analysis on the computers at NERSC at the time. And so we thought it was very fitting to name this computer after Saul, because it's the first machine that NERSC has deployed that we've been designed from the ground up to meet the needs of these experimental data sources as well as our traditional simulation workload. So one of the things that happened when our director called Saul up and said, can we name this machine after you? He said, sure, but I have one condition, and that is that you don't make our users type SSH Perlmutter.nersc.gov, they have to type SSH Sol.nersc.gov. We were very happy, and Saul was very happy. So that was a good thing. So I've talked to you today about our Perlmutter machine, which is coming next year at NERSC. It's going to be a Cray Shasta system. It will be about 3 to 4 times the aggregate performance of Cori, which is our current machine. As I mentioned, it's the first system that's really designed to meet the needs of large-scale simulation as well as experimental data analysis. And it will have GPU-accelerated nodes as well as CPU-only nodes. It will be based on the Cray Slingshot network, which is, as I mentioned, is really designed for high-performance computing. It will run applications at scale. It's high bandwidth, it's low latency, and it's also Ethernet compatible. And we'll also have a really cool flash file system. As I mentioned, there will be a large application readiness program to help users get up and running on the machine. That will have a component of simulation applications as well as data and analysis applications, as well as up and coming deep learning applications. So this is a view from our building in Berkeley. Just over there to the left is the city of San Francisco, and just behind the building, you can't really see it here, is the Golden Gate Bridge. So we certainly have the best view of any national lab, and we are hiring, so if you're interested, there's a URL down there at the bottom. Thank you very much for your attention.